The harbor at Samos came to life before the sun had fully cleared the water. In the gray-gold hour before full morning, when the sky over the Aegean held its color like a shallow bowl holds light, the docks were already moving with the slow, deliberate traffic of commerce, ropes drawn through iron rings, the low creak of hulls adjusting to the tide, men calling across the water in the several languages of the Mediterranean world, cedar and pitch, salt and fish meal, and beneath all of it, the particular smell of timber that has been at sea, which is different from timber that has not, carrying in its grain some record of every port it has visited. The island of Samos in the 6th century before the Common Era was not a quiet or marginal place. It was prosperous, well positioned in the trade routes that connected Greece to the older civilizations pressing in from the east and south, and its harbor reflected that position in the variety of vessels that arrived and departed across its deep water. Phoenician traders came with dyes and glass. Egyptian ships moved slowly with grain and stone carvings, and the particular goods of a civilization that measured its age not in centuries, but in something longer. A boy who spent time at those docks, watching the unloading, listening to the conversations held in gestures between men with no common language, would have understood from an early age that the world was considerably larger and stranger than any single island's customs could contain. It was into this world that Pythagoras was born, probably sometime around 570 before the Common Era, the son of a craftsman named Menasarchus, who worked with gems, a cutter and engraver of stones for rings and seals, a man whose trade required the kind of patient, precise attention to form and proportion that leaves its mark on a household. The dates are not certain. Very little about the historical Pythagoras is certain, and this is the first thing to understand about him. He is a figure who stands at the intersection of what can be verified and what has been believed, and both of those things are in their different ways true about him. The scholar Walter Burkert spent much of his career trying to separate the historical Pythagoras from the figure that centuries of devoted followers and hagiographic tradition had accumulated around his name, and what Burkert found, after that careful sifting, was that the historical core was smaller than the legend, and that the legend was not therefore false. It was a different kind of truth, the truth of what a tradition needs its founder to have been, which reveals something about the tradition that no biography could reveal about the man. The mythologized Pythagoras and the historical one are not in competition. They are different objects, answering different questions, and the philosopher who holds them both in view, without forcing either to dissolve into the other, is practicing a kind of intellectual patience that the Pythagorean tradition would have recognized and approved. The stories that accumulated around him are remarkable in their scope and their variety. He was said to have been the son not of the gem engraver Menasarchus, but of the god Apollo, a claim that was made about the best of philosophers in antiquity, as if genius required a divine paternity to be fully accounted for. He was said to have been seen simultaneously in two cities on the same day. He was said to have a golden thigh, a detail so strange and specific that its very specificity argues against anyone having invented it casually. He was said to remember his previous lives, all of them, stretching back through incarnations as a fisherman, a philosopher, a soldier, a plant, with a clarity that ordinary memory does not approach. These stories were told not by enemies trying to discredit him, but by followers who loved him, and they were told with the particular conviction of people who believed the stories were true. Metamycosis, the transmigration of the soul through successive lives, passing from one body to another across the long arc of its journey toward purification, was the Pythagorean doctrine that most shaped how the brotherhood understood itself and its work. The soul was understood to be older than any single life. It had been here before. It carried with it, beneath the surface of ordinary memory, some residue of what it had encountered in previous incarnations, and the philosopher's task was partly to recover that buried knowledge, to remember Mnemonik in the old Greek sense that Plato would later make famous, what the soul already contained. Whether this doctrine came to Pythagoras through contact with the Orphic religious traditions of Greece, or through whatever he encountered in Egypt and Babylon, or whether it arose in him as something genuinely his own, is a question that scholars have not resolved, and perhaps cannot resolve. It appears in Indian philosophical traditions that have no clear historical connection to the Greek world, and this either means the idea traveled by roots whose evidence has not survived, or that certain metaphysical intuitions about the soul's nature arise independently when human minds sit long enough with the question of what they are and where they come from. The young Pythagoras, Pilation ide aring, and wad portisibilla, and when human minds sit long enough with the question of what they are and where they come from, that by the accounts that came down through Iamblichus and Porphyry, who wrote their biographies of him 5 and 6 centuries after his death, and so must be read with care, though their accounts preserve traditions worth attending to, did not remain long on the island of his birth. He traveled. He went to Egypt, where he studied, according to those accounts, with priests at Memphis and at Diospolis, spending years in the temples, learning whatever it was that the priests of Egypt taught to those foreign students who demonstrated sufficient patience and seriousness to be received. He went to Babylon, where the Chaldeans, the astronomer priests whose knowledge of celestial patterns was the most systematic in the ancient world, showed him what they knew about the movements of planets and the relationships between mathematical ratios and the ordering of time. He went, some accounts say, even further east. There is a habit, still not fully abandoned, of treating Greek rationalism as something that arose in isolation, a sudden flowering of clear thought in the 5th and 6th centuries that separated itself from the mysticism and superstition of the surrounding cultures and invented, essentially from nothing, the practice of philosophical argument and mathematical demonstration. The biography of Pythagoras, even in its legendary form, resists this. The philosopher who would articulate the deepest connection between number and reality spent years as a student in the oldest literate civilization in the world, in a culture whose mathematics and whose cosmology had been developing for millennia before any Greek philosopher drew a triangle in the sand. What exactly Pythagoras learned in Egypt, and how much of what he later taught can be traced to those years, cannot be established with certainty. What can be established is that he went, that a thinker who would teach that reality is mathematical in its deepest structure chose to sit before Egyptian priests who drew geometric figures in the dust and flickering oil lamp light in the silence of a temple whose walls had been carved with mathematical knowledge longer than anyone present could remember. Imagine that room, not the grand reconstruction of a historian, but the specific sensory fact of it, the smell of oil burning in clay lamps, the dry warmth of the Egyptian interior, the sound of a stylus moving across a clay tablet, and a young man from a prosperous Aegean island sitting very still in the presence of knowledge he had traveled a long way to find. The priest draws a right triangle. He indicates its sides. He shows, perhaps by demonstration, perhaps by the accumulated practical wisdom of builders who had been measuring and cutting stone for centuries, the relationship that holds between those sides. The student copies the proportions with careful hands, pressing the mark of the figure into memory as much as into clay. Something passes between teacher and student in that room that is not merely information. It is the recognition that the world has structure and that structure can be read. This is perhaps the most important thing the stories tell about Pythagoras, that his philosophy, whatever else it was not inherited from a single tradition, but drawn from many, tested against many, and assembled by a mind that had been willing to travel to its sources. By the time Pythagoras arrived in southern Italy, in Croton, the prosperous Greek colony in what is now Calabria, he had been gone from Samos long enough to have become someone whose biography had already outrun easy summary. He was in his middle years. He carried the authority of a man who had seen more of the world's intellectual inheritance than almost anyone he was likely to meet in any single city, and he carried it with the kind of quiet certainty that is more persuasive than urgency. What he founded in Croton was something that no existing category quite fitted. It was a school, in the sense that people came to it to learn. It was a religious community, in the sense that its members observed dietary rules: no beans, no meat in at least some formulations, a series of prohibitions whose rationale was not always made explicit, and undertook practices whose purpose was understood to be the purification of the soul as much as the education of the mind. It was a political body in the sense that the members of the Brotherhood held positions of influence in the life of the surrounding city and brought to civic questions the particular perspective of people who had spent years contemplating ratio and proportion and the nature of order. It was something like a monastery, something like a philosophical academy, something like a sect. The traveler arriving at its gates at dusk, having heard stories about the figure at its center and the community that had gathered around him, would have stood for a moment in that threshold light, not quite darkness, not quite day, wondering which of those things he was approaching and whether the category mattered. The Brotherhood at Croton admitted both men and women, which was unusual enough in the ancient world to be worth pausing on. The Pythagorean community was one of the few intellectual communities in antiquity in which women are recorded as having participated as full members, as thinkers and teachers rather than as peripheral figures. Theano, who may have been Pythagoras's wife or his student or both. The sources disagree and may be describing different people, is credited with Pythagorean writings and with the transmission of the tradition. The community ate together in the evenings, shared in common, spoke with deliberate care. Meals were conducted in something close to silence, or with the kind of minimal conversation that does not interrupt the quality of attention that shared silence creates. The only sounds in the long room on a typical evening might have been the soft movement of shared dishes, the settled breathing of people who had spent the day in serious intellectual work, and somewhere along the table, barely audible, the low hum of a melody someone was quietly sustaining, not quite music, not quite silence, something between. The authority that Pythagoras held in this community was of a kind that later traditions would find difficult to classify, and in some cases, difficult to approve. The Socratic tradition that would develop in Athens, a tradition deeply influenced by Pythagorean thinking, even where it departed from it, held that philosophical truth must be arrived at through argument, through the careful mutual examination of positions, through the dialectic in which every claim is submitted to scrutiny, and the one that survives scrutiny has earned its place. The Pythagorean tradition, at least in its earlier form, operated on a different model. The authority of Pythagoras was not dialectical, it was revelatory. When a dispute arose within the community about a philosophical or mathematical question, It was not unusual for it to be resolved not by the production of a new argument, but by the simple statement that the master himself had spoken on this matter. Asterisk, autos ipha, asterisk, in Greek, he himself said it, and the room would fall still, the argument dissolving not because it had been answered, but because it had been superseded by an authority whose presence, though physically absent, filled the space entirely. This model of philosophical authority makes modern readers uncomfortable, and it should, because it is genuinely different from what most Western philosophy has since understood itself to be doing. But it is worth sitting with the discomfort long enough to understand what this model offered that the dialectical one does not, at least not easily. The Pythagorean community did not only want to know the truth about mathematics and the soul, it wanted to be transformed by that knowledge. It wanted the understanding of ratio and harmony and the soul's journey to change how its members lived, how they ate, how they held their bodies, how they moved through time. For that kind of knowledge, the kind that reaches all the way down into practice, something more than a persuasive argument may be required. It may require the example of a life. It may require the sustained presence of someone whose way of being in the world embodies the doctrine rather than merely asserting it. The asterisk autos ipha. Asterisk is not only an appeal to authority as a substitute for thinking, it is an appeal to a specific kind of knowing, the kind that is demonstrated in how a person lives, not only in what they can defend in argument, and that kind of knowing has its own integrity, whatever its epistemological limitations. The Pythagorean initiates went through a period of preparation before they were admitted to full membership that varied in different accounts, but was consistently described as involving a sustained period of silence. 2 years, some sources say, 5 years, others. The new member would attend the community's gatherings, listen to the teaching, observe the practices, take in everything that was offered, but would offer nothing back in speech, no questions, no responses, no demonstrations of cleverness or understanding or disagreement, just attendance, patient and extended, on what was being said and done. This was not understood as punishment or hazing. It was understood as education of a particular kind, the education that happens when the part of the mind that is busy composing responses is compelled to be still long enough for a different quality of attention to develop. What that attention is like, and what it makes available that ordinary conversational attention does not, the Pythagoreans believed was something that could not be fully explained to someone who had not undergone it. It had to be arrived at through the practice itself, the way the ear arrives at its ability to hear the consonants of the perfect fifth, not through being told what the fifth is, but through listening to it repeatedly with sustained care. The legends continued to accumulate long after Pythagoras died. Exactly when and how he died is itself disputed, accounts ranging from natural death in old age to death in political violence when the Brotherhood's influence provoked a reaction in the surrounding community. The philosophical tradition he founded kept spreading and transforming. His followers became known throughout the Greek world as a distinct intellectual community. His ideas about number and harmony and the soul entered the philosophical mainstream through Plato, who had spent time with Pythagorean thinkers in southern Italy before writing his dialogues, and who carried the Pythagorean conviction that mathematical structure is not a tool human minds invented, but a reality the cosmos itself embodies into some of the most influential philosophical texts ever written. Through Plato, the Pythagorean impulse entered the Western philosophical tradition and has not left it. The specific details of what Pythagoras himself taught as distinct from what later followers attributed to him, remain genuinely uncertain. The Pythagoreans themselves maintained an inner circle of teaching that was not to be written down or shared with outsiders, and much of what was eventually written was written by followers working from oral tradition, decades or centuries after the source. Aristotle, who is the earliest and in many ways the most reliable external reporter, writes about the Pythagoreans rather than about Pythagoras specifically, as if even by his time, a century and a half after the philosopher's death, the tradition had become more accessible than the man. What Aristotle reports is enough to suggest that the core doctrines about number, harmony, and the soul were genuinely early, genuinely Pythagorean in some foundational sense, even if the specific formulations evolved in the telling. To sit with the uncertainty about Pythagoras is not to conclude that nothing can be known. It is to understand that what can be known takes a particular form. There is the physical world from which the philosophy came, a prosperous Aegean island, a gem engraver's household, the busy harbor with its arriving ships, and its promise of everything the world beyond the island contained. There is the tradition of seeking, the journeys to Egypt and Babylon, the years in temple and observatory, the patient accumulation of mathematical and cosmological knowledge from the oldest civilized cultures the Greek world had contact with. There is the community that was built in southern Italy, with its combination of intellectual seriousness and shared daily discipline that no existing institution quite resembled, and that would not be fully replicated until Plato, drawing explicitly on what the Pythagoreans had done, built the academy in Athens. And there is the legend, the god-touched birth, the golden thigh, the memory of previous lives, the authority that filled a room in the form of 3 Greek words. He himself said it. None of these things is the whole picture. Together, held without forcing any one of them to be more definitive than it is, they constitute what it is possible to know about a figure whose influence on philosophy, mathematics, and Western thought about the relationship between order and beauty has been continuous for 25 centuries and shows no sign of concluding. The legend matters. The historical uncertainty matters. The physical world of the harbor and the temple and the long shared meal matters. All of them are true in different registers, and the question of how a mind holds multiple registers of truth simultaneously is itself, in a deep sense, a Pythagorean question. By the time the philosopher had been in Croton long enough for the brotherhood to settle into its daily rhythms, the morning study, the shared labor, the evening meal, the practice of looking back over the day's actions before sleeping, what had been established was something genuinely new, and yet something that people who encountered it recognized from traditions they already knew. It was the kind of community in which a life devoted to understanding was inseparable from a life shaped by discipline and practice and shared commitment. The mathematics and the music and the dietary rules and the silence were not separate activities held together by the accident of a single teacher's preferences. They were expressions of a single conviction that the world is ordered according to mathematical principles that the prepared and patient mind can perceive, and that perceiving them, genuinely perceiving them, rather than merely asserting them, requires a quality of attention that most lives do not cultivate, and that cannot be cultivated alone. The traveler who arrived at the gates of the Brotherhood at dusk, after walking for perhaps a day from the nearest city, would have seen lights in the windows of a compound that was neither quite a temple nor quite a school, and would have heard perhaps the faint sound of a single sustained note coming from somewhere inside, a voice or a string instrument holding a tone in the evening air. The traveler would have known something about the man who had founded this place, because stories about Pythagoras had spread throughout the Greek world of Magna Graecia and across the water to the older Greek cities, and the stories were not small stories. They were the kind that make a person stop walking and reconsider the direction they are going. But knowing the stories and standing at the gate of the place they describe are different things, and in the space between them, a specific kind of uncertainty opens. Not fear, exactly, and not quite excitement, but something in the neighborhood of both. The sensation of being on the edge of something that has not yet declared its nature. A knock on a door is a small thing. In most lives, it commits nothing. The door opens or it does not, and the person who knocked either enters or turns back toward the road. But there are knockings whose full significance is only legible in retrospect, when the life that followed has made clear what the life that preceded it would not have contained. Whether to knock was the question the traveler held in the threshold light, in the specific moment before deciding, when the compound was simultaneously both open and closed, both a school and a temple, both a possibility and a commitment, and no adequate word had yet been found for whatever it was that was being built inside. The lights in the windows held. The sustained note continued, barely audible, from somewhere within. The evening air of Magna Graecia moved in from the water, carrying its mixture of sea and pine, and the ordinary life of a prosperous coastal city, and the traveler stood in it, and the question hung in the air, as questions of this kind always do, not demanding an answer, not refusing one, only waiting, with the patience of something that has been waiting for longer than this particular evening, and will continue to wait, in one form or another, for longer still. Aristotle was sitting in the Lyceum on a morning in Athens, some 200 years after Pythagoras had lived, and he was reading aloud from a text that no longer exists. The original words of the Pythagoreans had survived in fragments, in summaries, in reports handed down through generations of students who had learned from students who had learned from students, the chain growing longer and the source growing quieter with each passing decade. What Aristotle read, and what he then set down in his own words, was this: the Pythagoreans held that the principles of numbers are the principles of all things. He wrote it plainly. He did not ornament it or qualify it into softness. The principles of numbers are the principles of all things. And because Aristotle was a philosopher of extraordinary precision, a man who spent his life making careful distinctions between categories and kinds, the very plainness with which he recorded this claim is its own kind of testimony that the idea was genuine and genuinely strange, and could not be reduced to anything simpler without losing what it actually meant. Aristotle himself did not agree with the Pythagoreans. He had his own account of what things are made of, and it did not involve numbers as first principles. But he understood the claim well enough to preserve it, and to take its difficulty seriously, and in doing so he became the bridge across which one of the most unusual ideas in the history of thought has reached every century since. The claim was not that numbers are useful for measuring things. It was not that numbers are convenient abstractions that help the mind organize what the senses deliver. The claim was something older and stranger than that number is the substance from which all existing things are made, that the principles which govern how numbers behave are the same principles which govern how everything behaves, and that if one wished to understand why the world is the way it is, the place to look was not into matter, but into ratio, into proportion, into the deep structure of mathematical relationship itself. To feel how strange this is, it is worth sitting with it for a moment. The ordinary assumption, an assumption so ordinary it barely seems like an assumption, is that numbers are human inventions. One counts 5 stones, and the 5 is a label applied to a group of real, heavy, stone-colored things. The stones are real. The 5 is a convenience. The world contains stones. The mind supplies the number. This is the picture most people carry, and it is so familiar it barely registers as a picture at all. The Pythagoreans saw something else entirely. For them, the 5 was not a label applied to the stones. The 5 was prior to the stones. The mathematical structure, the ratio, the proportion, the limit that gives a thing its specific form rather than some other form. This was what the thing actually was, in its deepest nature. The stone's weight, its density, its resonance when struck. All of these were, in the Pythagorean account, expressions of numerical relationship. The number was not added to the thing. The thing was the number, wearing the temporary costume of stone. This is the philosophical distance between Pythagoras and the Ionian philosophers who came before him. Thales had said the first principle was water. Anaximenes had said it was air. Heraclitus had said it was fire, understood as a living process of transformation. These were all material answers to the question of what things ultimately are, one kind of physical stuff giving rise to all other physical stuffs. The Pythagorean answer was not material at all. It was structural. The first principle was not a substance, but a relationship, not a stuff, but an order. Aristotle found this genuinely puzzling, and his puzzlement is worth attending to. He asked, in the metaphysics, how numbers could be the causes of things. In what sense does the number 5 cause a group of stones to be 5? How does mathematical structure produce physical substance? He did not find a satisfying answer in the Pythagorean texts available to him, and he said so. But the question itself, the question of why mathematical structure should be real in a way that goes beyond human counting, has not been answered in the centuries since, and philosophers and mathematicians are still sitting with it, still uncertain, still honest about the difficulty. What the Pythagoreans understood by number was not what the word brings to mind in a modern context. The Greek term was arithmos, and arithmos was not the abstract, context-free quantity that fills modern mathematics, the kind of number that floats free of everything, that is equally at home, measuring the distance between galaxies and the number of apples in a bowl, that has been stripped of every quality except pure quantity. Arithmos was always a number of something. It was always embedded in a specific arrangement, a specific proportion, a specific pattern of relationship between particular things. The number 3, in this understanding, was not simply the successor of 2 and the predecessor of 4. It was the number of the triangle, the first shape that can enclose a space, the first number that has a genuine geometric life. It carried its triangularity with it, even when no triangle was being drawn. The number 4 was the number of the square, of solidity, of the 4 directions that divide the world. These were not decorative associations, not the kind of number symbolism that one might find on a calendar. They were, for the Pythagoreans, genuine features of what these numbers were, qualities intrinsic to the arithmos itself, not added by human imagination. This is the qualitative dimension of Pythagorean number philosophy, and it is the dimension that modern mathematical thought has most completely set aside. When a contemporary mathematician works with the number 3, she works with a formal object whose meaning is entirely exhausted by its structural relationships to other formal objects. 3 is greater than 2, less than 4, the square root of 9, a prime. Nothing about the concept of triangle belongs to 3 unless a geometer explicitly imports it. The formalization that makes modern mathematics so powerful is precisely the stripping away of every quality that does not reduce to structure. The Pythagoreans had not yet made that stripping. For them, the stripping had not yet occurred, and they might have resisted it if it had been proposed, because what they were doing was not trying to construct a formal system. They were trying to perceive the nature of things. And in the nature of things as they found them, qualities and quantities were not yet separated. The three had its triangularity, the way a stone has its weight, not by convention, not by association, but by nature. And this quality-bearing sense of number shaped the most sacred symbol in Pythagorean philosophy. It was not a word, and it was not a god, and it was not a law carved in stone. It was a diagram, 10 small points arranged in rows, 1 point at the apex, then 2, then 3, then 4 along the base, forming a perfect equilateral triangle. The Pythagoreans called this arrangement the tetractys, and they swore their most solemn oaths by it, not as a convention of legal practice, but because they believed it contained, in its 10 points and their proportions, the mathematical structure of everything that exists. The tetractys was not merely a sacred object, it was a demonstration. 1 plus 2 plus 3 plus 4 equals 10, the first 4 integers, summing to the number the Pythagoreans considered perfect, the number that contains all things. But the 4 rows were not just a way of arriving at 10. Each row had its own identity. The point at the top, the 1, was the source, not yet a number in the ordinary sense, but the principle from which number emerges. The 2 points below it generated the line, the first extension of the point into space. The 3 points of the next row generated the plane, the first surface. The 4 points of the base generated the solid, the three-dimensional world in which human beings live and breathe. From 1 to 4, from point to solid, the entire geometry of physical existence unfolded in 4 steps. A Pythagorean student, learning this for the first time, was invited not to memorize it, but to arrange it. Small, smooth stones on a flat surface, 1, then 2, then 3, then 4, and to sit back and look at it as if the arrangement were a question rather than an answer. The rows had ratios between them, 1 to 2, 2 to 3, 3 to 4. And these ratios were not only geometric, they were also, as the Pythagoreans had discovered through their study of the vibrating string, musical. The ratio 2, 1 was the octave. The ratio 3, 2 was the perfect fifth. The ratio 4, 3 was the perfect fourth. The 3 primary consonances of music, the intervals that the ear recognizes as most purely harmonious, were all contained in the 4 rows of the tetractys. The diagram was not a metaphor. The Pythagoreans were not saying that music is like a triangle, or that harmony resembles proportion. They were saying that the tetractys contains the mathematical principles of both geometry and music, because geometry and music are 2 expressions of the same underlying numerical reality, and that underlying reality is what the tetractys actually is. To swear by the tetractys was to swear by the mathematical structure of the universe, to invoke as witness not a personal deity, but the impersonal law written into the proportions of things. And there is something in this that is both older and stranger than ordinary religious oath-taking. It is the invocation of reality itself as guarantor of truth. What could break such an oath? Only the dissolution of mathematics, the cessation of ratio, the end of proportion, and that, in the Pythagorean understanding, would be the end of everything, not merely the end of the agreement being sworn to. The Pythagorean metaphysical picture had at its deepest level a polarity, 2 opposing principles from which all number, and through number all things, were understood to arise. One of these principles was called the one, the tehen, and it was associated with limit, with form, with the clarity that gives a thing its definite character rather than leaving it in vague indefiniteness. The other principle was the indefinite dyad, associated with multiplicity, with extension, with the unlimited and the flowing, the principle that takes the limit imposed by the one and spreads it outward into the manifold of existing things. These were not numbers in the ordinary sense. They were the conditions for number. The one was not the numeral one, but the source from which counting begins, the act of positing a unit, of drawing a boundary that distinguishes this from that. A teacher, drawing a single point in the dust, might say this is the one, not the numeral one, not the first bead on an abacus, but the principle of unity itself, the act of gathering into a single definite thing, whatever would otherwise remain formless and without boundary. And the student watching the point would understand that it is a demonstration, not a definition, that the dot in the dust is pointing at something the dust cannot contain. The indefinite dyad is harder to feel because it is by nature the principle of difficulty, the unlimited, the many, the principle that resists the closure of the one. It is not two in the sense of the numeral two, but the principle of two-ness, of the emergence of the other, of the movement away from unity into multiplicity. The dyad takes the definite unit posited by the one and generates from it the series of numbers 2, 3, 4, and outward by a kind of indefinite proliferation that the one's limiting principle then shapes into specific, structured, countable things. From this tension in the Pythagorean account, all number arises, and from number, all things. The cosmos is not a product of material collision or divine will, but the outcome of the interaction between limit and the unlimited, between the principle of form and the principle of extension, played out through the medium of mathematical relationship. Plato, who spent time with Pythagorean philosophers in southern Italy, and who remained deeply influenced by this tradition throughout his long working life, would later incorporate this generative tension directly into his account of how the universe was made. The world soul in the Timaeus, the principle through which the demiurge animates the cosmos, is constructed precisely by dividing and arranging according to the ratios that govern harmonic tuning. The cosmos, in Plato's account, is not merely mathematically ordered, it is musically proportioned at its deepest structural level, and that proportioning is the Pythagorean doctrine wearing the costume of a creation myth. But before Plato, and within the brotherhood itself, the teaching had already distinguished between kinds of number in a way that reveals how far the Pythagorean understanding was from simple counting. Odd numbers were associated with limit, with definiteness, with the divine, with the principle of completion. The odd number closes on itself in a way the even number cannot. Divide an odd number, and one part is always greater than the other, the asymmetry preserving something of the original unity. Even numbers were associated with the unlimited, with divisibility, with the mutable and the flowing. Divide an even number, and the two halves are perfectly equal. The unity dissolves into mirror images of itself, nothing left over, the original wholeness replaced by pure symmetry. This is not number symbolism in a casual or decorative sense. It is a philosophical claim about the qualitative character of mathematical objects, the claim that odd and even are not mere properties of numbers, but expressions of the fundamental cosmological polarity between limit and the unlimited. The fact that 7 is odd and 8 is even is not an arbitrary feature of their positions in the sequence. It is an expression of their natures. The 7 belongs to the world of limit and form. The 8 belongs to the world of extension and multiplicity. To understand number is, in this account, to understand the fundamental structure of what exists, not by analogy, not by metaphor, but directly, because number is what things are. Two members of the Brotherhood, debating one evening whether 10 was perfect by nature or only by convention, would have found themselves in a conversation that was not really about 10 at all. It was about whether mathematical properties are discovered or invented, whether the perfection of 10 as the sum of the first four integers, as the completion of the tetractys, as the number that gathers in itself the foundations of geometry and harmony, was a feature of reality that human beings had noticed, or a feature of human counting that human beings had projected onto reality. The debate would not have ended cleanly. Both of them would have known the arguments, and the end, if there was an end, would probably have been the thing that serious philosophical conversations sometimes arrive at, not resolution, but a shared quieting, both of them resting in the question together, the question proving larger than either of the positions they had brought to it. In a shaft of morning light, inside the Brotherhood's meeting hall, a senior member tracing the ratio 2, one with his hands in the air, one long interval, then its half, would have been doing something that looks from the outside like a simple gesture of measurement. But in the context of the Pythagorean understanding, the gesture was more than measurement. It was an act of contact with structure. The ratio 2, 1 was not a notation. It was not a shorthand for something else. It was the thing itself, the mathematical relationship that, when expressed in sound, produced the octave, and when expressed in geometry, generated the doubling of a line, and when expressed in cosmology, organized the structure of the heavenly spheres. To trace it with one's hands was to touch the pattern that runs through all of these manifestations at once. This is the feature of Pythagorean thought that is most difficult to translate into modern terms, because the modern understanding has so thoroughly separated the domains that the Pythagoreans held together. In the Pythagorean picture, music and mathematics and astronomy and philosophy were not different disciplines that occasionally borrow each other's methods. They were different windows onto the same room. What the mathematician expressed as ratio, the musician heard as consonance, the astronomer observed as planetary proportion, and the philosopher contemplated as the underlying structure of being. The tetractys was the room, seen from all four windows at once, and the Pythagorean curriculum at Croton was built on this unity. The four subjects that would later be grouped together as the quadrivium, arithmetic, geometry, music, and astronomy, were in the Pythagorean teaching not four distinct fields, but four aspects of a single inquiry into mathematical structure, at different scales and in different materials. Arithmetic was the study of pure number. Geometry was the study of number in space. Music was the study of number in time, expressed through sound. Astronomy was the study of number in the vast time and space of the cosmos. The same ratios appeared in all four. The student who understood the octave in music would, on this account, understand something true about the orbits of the planets, because both were expressions of the same mathematical law. Late at night in Croton, a mathematician staring at a clay tablet covered in numerical ratios would have been doing something that in the Pythagorean understanding went beyond calculation. The ratios on the tablet were not inventions. They were not the work of the mathematician's mind imposing order on a neutral world. They were discoveries, findings, the uncovering of patterns that existed before the tablet, before the mathematician, before any human mind had thought to look. The feeling beneath the calculation, the sense that the symbols are pointing at something the symbols cannot quite contain, was not mysticism added to mathematics. It was the honest recognition that the symbols are representations of something real, and that the reality they represent is larger than the representation. This sense of mathematical objects as independently real, as things that exist, whether or not any human mind is currently counting them, is not exclusively ancient. It remains in the 21st century one of the genuinely open questions in the philosophy of mathematics. The position that mathematical truths are discovered rather than invented, that the relationship between the diagonal of a square and its side is what it is, regardless of whether any geometer has yet drawn the square, is a position that serious contemporary philosophers defend with careful arguments. It is not a relic, it is a live dispute, and the Pythagoreans were the first to press the claim into explicit form, the first to insist that mathematical relationship is not a human construction, but a feature of reality to which human mathematics is the best available approach. The strangeness of the claim does not diminish on close examination. It grows. If number is real, genuinely, independently real, then what kind of thing is it? It has no location. It has no weight. It cannot be touched or tasted or seen. And yet the ratio 3:2, wherever it appears, produces the same effect, a perfect fifth, a proportioned rectangle, a harmonic interval in the spacing of heavenly bodies. The ratio does not depend on which string is plucked or which two things are being compared. It persists through every material instantiation, identical in all of them, changed by none of them. It has the persistence and the invariance of something that simply is, regardless of what happens around it. The Pythagoreans, living with this claim daily, found in it not an abstraction, but a kind of company. The mathematical structure of things was not cold or inhuman. It was the form of the real, the shape that reality takes when the particular and the accidental are set aside and the underlying pattern is attended to. To study mathematics was not to move away from the world into a system of symbols. It was to move more deeply into the world, past the surface of particular things, into the structural layer where things are what they are, rather than what they merely appear to be. There is a kind of attention that mathematical contemplation requires and produces. It is not the alert, scanning attention of someone looking for danger, or the warm, expansive attention of someone in conversation. It is quieter than both of those. It is the attention of someone who has stopped imposing and begun receiving, who has set aside the question of what the pattern ought to be in order to see what it actually is. The Pythagoreans knew this quality of attention well. They cultivated it deliberately. The silence required of new initiates, the careful daily observance of proportion in diet, and in speech, and in the ordering of the day, these were not obstacles to mathematical study, but preparations for it. The soul that has not learned to be still cannot perceive what is still. The mind that is full of its own noise cannot hear the ratio. When a Pythagorean student, working alone at the edge of the community's compound, arranged the 10 stones of the tetractys on a flat piece of ground and sat back to look at them, what was happening was not merely a contemplative exercise. It was, in the Pythagorean account, a moment of alignment. The pattern in the stones corresponded to the pattern in the vibrating string, and to the pattern in the heavens, and to the pattern in the soul of the student looking at it. To perceive the tetractys with genuine attention was to perceive the same structure in 4 places simultaneously, or rather, to perceive one structure through 4 of its expressions. The student and the stones and the music and the stars were all, at that moment, obeying the same law. The recognition of this was not a metaphysical hypothesis to be evaluated. It was an experience to be had, and the careful arrangement of the stones was the occasion for having it. The Pythagorean community was organized around the conviction that how one lives and what one is capable of understanding are not separate matters. The soul that has spent the day in disorder, in inconsistency, in excess, in the kind of fractured attention that ordinary life encourages, is not the same soul that can sit down in the evening and perceive mathematical proportion clearly. The ordering of daily life, the careful meals, the shared silences, the practice of reviewing the day before sleep was understood as the tuning of an instrument. The instrument was the soul. The music it was being tuned to play was the perception of mathematical truth. This is the sense in which the Pythagorean philosophical project was not divisible into a mathematical part and an ethical part and a religious part. For the Brotherhood, these were not three projects but one. To understand number rightly was to live rightly, because the life well ordered was the soul capable of perceiving order, and the soul capable of perceiving order was living in alignment with the mathematical structure that underlies all things. The triangle in the tetractys was not a symbol of the soul's aspiration toward the one. It was a diagram of what the soul is trying to become, a proportioned, limited, structured thing, shaped by the same ratios that shape the consonant interval and the well-turned orbit. There is something in this that resists the modern tendency to keep disciplines separate, to insist that mathematics belongs to one faculty, ethics to another, music to a third. The Pythagoreans had not yet made those separations, and living without them gave their thought a kind of wholeness that is difficult to recover from within the separated departments. When a number was good, when it was well proportioned, when it exemplified limit and form, it was good in the same sense that a musical interval was good, and a just action was good, and a well-ordered soul was good. The good was not a human evaluation added to a neutral fact. It was a mathematical property, as real as the ratio itself, as discoverable as the octave. And underlying all of it, the stones on the ground, the string vibrating over the wooden bridge, the careful arrangement of the daily schedule, the evening descent into shared silence, was the simplest and most radical of all the Pythagorean claims. That the structure of what is real is mathematical, that the world is not merely susceptible to mathematical description, as a geographer's map describes, but is not identical to a territory, that the map and the territory are at the deepest level the same, that to count, to measure, to attend to ratio and proportion in the specific way one quantity stands in relation to another, is not a human activity performed on a reality that does not care about it. It is participation in the fundamental nature of what exists. 10 points, 4 rows, 1 at the top, then 2, then 3, then 4, along the base, a triangle small enough to draw in dust, stable enough to swear an oath by, large enough, if the Pythagoreans were right, to contain the organizing principle of everything that has ever existed or ever will. A student arranges the 10 stones for the first time, sits back and looks. The ratio of the second row to the first is 2. 1. The ratio of the third row to the second is 3. 2. The ratio of the fourth row to the third is 4. 3. These are not 3 different ratios about 3 different things. They are 3 aspects of one mathematical structure, present in the 10 points arranged in the dust, present in the vibrating string across the room, present in the spacing of the heavenly bodies moving overhead, present in the proportioned silences of a well-ordered life. The student looks at the stones and finds, unexpectedly, that the stones seem to look back, not with eyes, but with the kind of patient, impersonal attention that belongs to things that simply are what they are, completely and without remainder, waiting only for a quiet enough mind to arrive and recognize them. In a street in the city of Croton, in the late afternoon of a day whose precise year no longer matters, a philosopher stopped walking. The sound that stopped him was coming from behind a wooden door, the rhythmic iron report of a blacksmith's work, hammer meeting anvil in the steady cadence of a craft being practiced without any thought of music. Nothing about the street was unusual. The light was the particular gold of a Mediterranean afternoon beginning to soften. Other people walked past without pausing, but something in the combination of those hammer blows, some quality in the way the successive strikes fell against the air of the street, held the philosopher where he stood in a way he could not immediately explain, the way a person sometimes stops mid-sentence, not because they have forgotten the next word, but because something just beneath the word is asking for attention. He stood and listened. The hammers went on, and in their going on, a pattern announced itself to him that was not quite sound and not quite thought, but something at the edge of both, the sense that the intervals between certain combinations of strikes felt right in a way that other combinations did not, that there was a difference between harmony and its absence, that the ear could detect long before any mind could name it. This is where the story begins, not in a library, not at the feet of a teacher, not in the organized stillness of contemplation, but in an ordinary street, with the smell of hot iron in the air, and a man standing still because the world had briefly, precisely, insisted on his full attention. The story the Pythagorean tradition tells about this moment is not fully accurate in its physics. The weights of hammers do not determine the pitch of the notes they produce in quite the way the story requires. The physical reality of what governs the pitch of a struck surface is more complicated and involves the material, the geometry, the point of impact in ways that the legend compresses into a cleaner claim. But this is the kind of inaccuracy that reveals something true by means of something simplified, and to correct the physics without first receiving what the story is doing would be to miss the whole point of what the story is doing. What the story is doing is this: it is placing the discovery of mathematical law at the origin of sensory experience, before any calculation has been performed, before any string has been measured, before any ratio has been named. The philosopher stops in the street, not because he has worked out a hypothesis, but because his ear has already found something his mind has not yet caught up to. The mathematics, when it arrives, will not be an imposition on the experience. It will be the experience, understood. This matters enormously to the Pythagoreans, because if the ear can detect before any calculation the difference between a harmonious combination of sounds and a dissonant one, if what we call beauty in sound is not a preference but a perception, then something extraordinary is implied. What the ear is perceiving when it hears a harmony as right is not an opinion, it is a fact about the structure of the physical world, a fact that has a precise mathematical description, a fact that was true before any human ear existed to notice it. The hammer stopped, then it started again. The philosopher remained where he was in the street, listening, as the light continued to soften around him, until the smiths inside eventually noticed him through the open window and stopped their work to ask what he wanted. What he wanted, though they would not have had words for this either, was to know why certain sounds are beautiful and others are not. And the first step toward an answer was already present in the question, that the ear knows the difference before the mind does, and that this fact is not evidence of the ear's unreliability, but evidence of something else entirely. The monochord was a simple instrument, a single string stretched taut over a narrow board, with a movable bridge that could be positioned precisely along the string's length to shorten the vibrating portion and raise the resulting pitch. It was not beautiful. It was not designed for performance or pleasure. It was designed for a single purpose that has more in common with a measuring instrument than with what most people mean when they say the word instrument. which is to say, it was designed to ask a question of the physical world and receive a precise answer in return. The question asked was this: if a string vibrates at a certain frequency and produces a certain note, what happens to that note when the vibrating length of the string is changed by a specific proportion? The answer it gave was, to anyone who had attended to it carefully, astonishing. Press a finger to the exact midpoint of the string, the point that divides it precisely into two equal halves, and pluck the shorter portion. The note that sounds is the same note as the full string's note, but higher. Not approximately the same note, not suggestively similar, but precisely, undeniably the same note, raised by exactly 1 octave. The ratio between the full string's length and the stop string's length is 2, 1. The ratio between the frequencies of the two notes is, correspondingly, 2, 1. The same number governs both. Stop the string at a point that leaves 2/3 of its length vibrating, and pluck. The interval between this note and the original is a perfect fifth, the interval that the ear receives as perhaps the most stable and open of all harmonic relationships, the interval that sounds as if it could continue indefinitely without ever needing to resolve, the interval that appears in the earliest surviving music of almost every culture that has been studied. The ratio of string lengths is 3:2. The ratio of frequencies is 3:2. Stop the string at a point that leaves 3/4 of its length vibrating, and pluck. The interval is a perfect fourth, slightly more closed than the fifth, slightly warmer, the interval that sounds like the fifth's quieter and more settled companion. The ratio is 4:3, 3 consonances, 3 ratios, and the numbers of those ratios are 1, 2, 3, 4. The first 4 integers, the integers whose sum is 10, the integers whose triangular arrangement in rows of 1, 2, 3, and 4 makes the tetractys, the most sacred symbol of the Pythagorean community. The same integers that appear in the symbol held up before their oath-taking appear in the ratios that govern what the ear hears as beautiful and right. This is not a coincidence the Pythagoreans are reaching for. It is a pattern the numbers themselves are exhibiting, and the instrument is simply the means by which the pattern becomes audible. A student sits with a monochord in the evening light. The board is narrow and plain, the string slightly worn from repeated use. He positions the bridge carefully at the midpoint, checks the placement by eye, then plucks the shorter section and holds very still in the ring of the note as it begins to fade. The same note as before, but higher, always, every time. Not sometimes, not approximately, but with the consistency of a law. He moves the bridge, he listens, he moves it again. What he is doing has the character of a conversation, question, answer, question again, except that the instrument does not choose its responses. The string does not consider. It simply tells him, with perfect reliability, what the physical world requires in this situation. And what the physical world requires in this situation turns out to be the same thing every time, governed by the same small numbers, in the same fixed relationships, without exception or variation. After enough of these conversations, the student sits back and looks at the string lying still along its board, the bridge in the position he has last left it, and he feels something that the word discovery does not quite capture. Discovery implies that something was hidden and has now been found. But what the string has shown him was not hiding. It was, in some sense, waiting to be heard, which is different, because waiting implies that the thing was already there, already formed, already true, and that the student's role was not to create it, but to arrive at the right position of attention, to receive it. This is the shift the Pythagoreans are making, and it is a more significant shift than it might initially appear. The claim is not that music follows mathematical rules. The claim is that the mathematical rules came first. The consonance is consonant because the ratio is simple. The beauty is beauty because the structure is ordered. The experience of hearing something as right and harmonious is, when understood correctly, the experience of perceiving a mathematical relationship, which means that what the ear is doing when it hears a harmony and receives it as beautiful is doing a kind of mathematics that bypasses the mind's explicit calculations and arrives directly at the result. The aesthetic experience is not separate from the mathematical one. It is not a pale emotional reflection of the mathematical one. It is the mathematical one, felt from the inside by a creature whose nervous system is sensitive to ratios in ways the creature itself rarely thinks to name. Two members of the brotherhood sit together in the fading light of an afternoon, a monochord between them. They are not performing. There is no one to perform for. They are moving the bridge slowly along the string, pausing at each position, listening to the resulting interval against the memory of the original note, and neither of them is speaking. The sounds arrive and pass. Some of them are dissonant, the bridge in a position where the resulting ratio is complex, the ear receiving the combination as unresolved, slightly effortful, pressing towards something that has not yet arrived. Some of them are consonant, the bridge in one of the positions corresponding to the simple ratios, the ear receiving the interval as settled, proportioned at rest. What the two of them are noticing, though neither would put it quite this way, is that the dissonant intervals feel like questions and the consonant intervals feel like answers. Not metaphorically, not approximately. The dissonant intervals generate in the listener an expectation, an almost physical sense of forward leaning, of something unfinished that the next sound is being asked to complete. The consonant intervals release that tension, not by canceling the sound, but by resolving it into a state of ordered proportionality, from which nothing further is required. Resolution is not silence. This is important. The consonant interval is still sound, still vibration, still the physical movement of air between the string and the ear. What makes it feel like rest is not the absence of sound, but the presence of a particular mathematical relationship between two sounds, a relationship in which the periods of the vibrations overlap cleanly, in which the system is governed by a small whole number ratio rather than a complicated one, in which the physical world is for a moment in a state of simple and proportioned order. To hear a harmony resolve is to perceive the difference between disorder and order through sensation alone. The ear knows. The knowing arrives before any calculation, before any understanding, before the mind has had time to form a single thought about ratios or proportions or the integers that generated them. The ear already knows that the interval has arrived at something right. The mathematics simply explains, after the fact, why the ear knew. A teacher draws on a wax tablet. He draws the number 2 and beside it, separated by a colon, the number 1. He says nothing for a moment, letting the student look at the two numbers in the relationship the colon establishes between them. Then he says, "This is the octave," not "this represents the octave," or "this can be used to calculate the octave." This is the octave. The interval and the ratio are the same thing, encountered from two different directions. The ratio as it appears to a mind working with numbers, the interval as it appears to an ear encountering the physical world. The student looks at the two numbers. They are as simple as numbers get, the simplest possible whole number ratio, after 1, 1, which is to say unison, which is to say not two notes at all, but one note sounded twice, 2, 1, one number twice the other, and the physical world, when organized in this proportion, produces what every human ear recognizes as a harmony so fundamental that it forms the basis of all subsequent harmonic organization, all scale building, all the complex music that would follow from this discovery across thousands of years and across every musical tradition that has taken the octave as its basic unit. He draws 3 and 2. He says the fifth. He draws 4 and 3. He says the fourth. He sets the tablet down and looks at the numbers, and the student looks at them too, and there is a silence in the room that is not the silence of nothing happening, but the silence of something having just become clear, in a way that makes further speech feel, for the moment, unnecessary. These are not large numbers. They are not complicated numbers. They are the kind of numbers a child encounters before the age of 5, counted on fingers, arranged in piles of pebbles, totaled in simple sums that take no effort and require no instruction. And yet these numbers, in these simple ratios, determine what the ear will receive as beautiful across every culture, every era, every context in which human beings have made or heard organized sound. The Pythagorean intuition that follows from this observation is radical enough that it takes time to feel properly. The intuition is not that music uses mathematics. The intuition is that beauty is mathematics, that what the ear hears as harmonious is precisely and only what a mathematician would recognize as proportioned, that the standard the ear applies when it hears a consonance as right is not a cultural convention or a trained preference, but a perception of a genuine mathematical property of the physical world. And if this is true of sound, if the ear, without being told, without being taught, without any conscious calculation, reliably and universally perceives the simplest mathematical ratios as beautiful, then the question the Pythagoreans cannot help asking is, what else might this be true of? If hearing is a kind of mathematics, is seeing, is touch, is the sense of rightness that sometimes arrives when a proof closes or a geometric figure reveals an unexpected symmetry, is the experience of beauty across all its forms the experience of a mind or a body perceiving mathematical order. This is the generalization. It does not arrive all at once. It builds slowly, each observation adding to a pattern that becomes harder and harder to dismiss as coincidence, until the Pythagorean philosopher is no longer asking whether mathematics governs beauty, but asking instead how far the governance extends. The student who has spent an afternoon with the monochord returns to it the following morning, and the morning after that. The string does not change. The bridge positions that produce consonances are exactly where they were the day before. The ratios hold. They hold the way the proportion of a circle holds, not because anyone has decided they should, not because a tradition has agreed to honor them, but because the physical world, at the level of vibrating lengths and resulting frequencies, simply is organized this way and has no alternative. There is something settling about this, not comfortable in the way of a chair or a warm room, but settling in a deeper sense, the sense that something has been confirmed that the mind suspected but had not until now seen demonstrated. The world has a structure. The structure is mathematical. The ear can feel the structure even when the mind has not yet named it. And the name, when it finally arrives, does not impose the structure but reveals it, labels what was already there, points at what the ear had already found. In the evenings, after the day's work of study and practice was done, members of the brotherhood sometimes gathered to perform what might be called musical investigations. The word performance is not quite right, and concert is not right either, and recital misses the point entirely. What they were doing was more like collaborative listening, 2 or 3 people with instruments, moving through intervals and combinations, attending to what each interval produced in the air between them and in the physical sensation of the vibration, comparing what was heard against what was known about the ratios involved, checking the correspondence between the mathematical prediction and the auditory experience. The remarkable thing was that the correspondence never failed. Wherever the monochord said there should be consonants, the ear heard consonants. Wherever the ratio was complex and the vibrations did not align cleanly, the ear heard dissonance, something unresolved, something pressing forward, something that wanted to move. The mathematics and the experience were one continuous thing, and the division between them was a division made by language, not by reality. One evening, a single member of the Brotherhood sat alone after the others had gone. He had a small lyre, which he held against his body rather than setting it down, and he was playing intervals softly, barely above a whisper, moving from one to the next with no particular intention, except the intention of attending to each one as it arrived and faded. He played the octave and let it ring. He played the fifth and held it in the air of the room. He played the fourth and felt its slightly more closed quality, the fifth's interior, its settled companion. Then he played a combination that the Pythagorean analysis would describe as dissonant, two notes whose frequencies stood in a complex ratio, whose vibrations did not resolve cleanly into each other, whose combined sound pressed slightly forward, incomplete. He held the dissonant combination and noticed what it felt like from the inside, the expectation it created, the sense of something unfinished, the physical quality of leaning toward a resolution that had not yet come. Then he moved one string by a half step, and the dissonance resolved into a fifth. The room, which had not been loud, went quieter with the resolution, not because any sound had stopped, but because the quality of the sound had shifted from pressing to arrived, from question to answer, from something reaching toward order to something resting in it. He sat with the fifth for a while. Then he played the dissonance again, and felt again the expectation it created, and resolved it again into the fifth, and sat again in the consonance. He did this several times, not to demonstrate anything, not to study the phenomenon in any formal sense, but because the movement from dissonance to resolution had a quality he found he wanted to experience repeatedly. The mild tension, then the settling, then the quality of rest that was not silence but structured sound, sound that had arrived at a proportioned relationship and was, for the moment, at ease with itself. The law behind the monochord experiments was not a law someone had invented. This requires saying carefully, because the modern ear has been trained to hear the word law in relation to mathematics and think of human-made rules, conventions established for convenience, categories imposed on a neutral reality that could have been categorized differently. The Pythagorean understanding is precisely the opposite. The ratio 2, 1 does not produce an octave, because the Pythagoreans decided to call whatever 2, 1 produces an octave. The ratio 2, 1 produces the octave, because the physical world, when organized in that proportion, vibrates in a way that the ear of every human being in every culture has received and will continue to receive as a harmony so fundamental it forms the foundation of all musical thought. The law was there before the Pythagoreans. The law was there before humanity. The string does not know about the Pythagoreans, and it does not care about them, and it will produce the same intervals when stopped, at the same proportions long after the last philosopher has put down the last pen. The discovery is a discovery of something that was always already the case, which is exactly what makes it feel, to the person who makes it, less like an invention and more like an arrival. Pythagoras paused in the street, and something stopped him. The law had been operating in that blacksmith's shop, and in every blacksmith shop, and in every vibrating surface, and in the motion of the air above every stretched string, since long before the street existed, or the city, or the island, or the civilization that named these things. The philosopher's presence was required only for the noticing, not for the fact. What came after the noticing, the careful measurement, the monochord, the systematic investigation of ratios and their corresponding intervals, the construction of a full scale by stacking the consonances in sequence, all of that is the work of following the first observation as far as it would go, and it goes very far. The Pythagorean scale built by stacking the ratio 3-2 repeatedly, moving upward by a perfect fifth at each step, then adjusting downward by octaves when the notes climb too high, produces a sequence of tones in specific proportioned relationships that the ear receives as a coherent musical world. The tones are not equally spaced. The steps between adjacent notes in the scale are not all the same size. The Pythagorean investigation found that this was not a flaw, but a feature. The unequal spacing of the intervals was itself a reflection of the mathematical structure underlying the system, a structure in which the ratios between steps fell into a small number of distinct types, each corresponding to a specific proportion of small integers. And then, at the end of the stacking process, when the circle of fifths had been completed, and the last fifth brought the sequence back, in theory, to the original note, the Pythagoreans found something that the mathematics required and that the ear could not quite accept. The final note generated by 12 successive perfect fifths did not land exactly on the starting note. It fell slightly short. The gap was small enough to be measured precisely. The ratio involved was a specific and slightly complex proportion, neither the 2, 1 of the octave, nor the 3, 2 of the fifth, but something between them, a small residual dissonance built into the structure of the system at its completion. This gap has a name, though the name belongs to a later period of musical history, the Pythagorean comma. It is the distance between where the circle of fifths closes in theory and where it closes in practice, the slight and ineradicable remainder that the system generates when it runs out its own logic all the way to the end. There is something philosophically interesting in this remainder, not threatening, not a crisis, but genuinely interesting in the way that a proof that almost closes is interesting. Interesting precisely because the almost is not an error, but a consequence of the mathematics itself. The system that produces the 3 primary consonances in ratios of perfect simplicity, the system that gives the ear the octave and the fifth, and the fourth in the most orderly mathematical form imaginable, is the same system that, when completed, finds that its last step does not quite meet its first. Order, pursued all the way to its conclusion, encounters a small and irreducible excess. The Pythagoreans did not experience this as a refutation of their view. A system that generates the primary consonances from the first 4 integers and reveals at its limit a small and precisely quantifiable remainder is still a profoundly ordered system. The comma is part of the order. It follows from the order as necessarily as the consonances do. What it perhaps suggests, if one is willing to sit with the suggestion rather than rushing to resolve it, is that mathematical order and perfect closure are not the same thing, that a structure can be deeply and genuinely orderly without fully coinciding with itself at every point. But this is a thought to return to, slowly, not to press. The comma is small, the consonances are primary, and the primary observation, that the intervals the ear receives as beautiful correspond precisely to the mathematical ratios the mind recognizes as simple, stands intact whether or not the circle of fifths closes perfectly. The generalization the Pythagoreans drew from the vibrating string to the wider world was not a reckless leap. It was a careful extension of an observed principle into domains where the same principle might be expected to operate. If the physical world organizes sound in accordance with mathematical proportions, and if the human nervous system is sensitive to those proportions in a way that produces the experience of beauty where the proportions are simple and the experience of dissonance where they are complex, then the natural question to ask of any domain of experience is whether the same structure might be operating there at a level the relevant sense can detect. For the Pythagoreans, this question extended naturally to the sky. The planets moved. Movement could be characterized in terms of speed and period and distance. Speed and period and distance were quantities. Quantities stood in ratios to one another. Ratios could be simple or complex. Simple ratios in the domain of sound produced consonances, intervals the ear received as harmonious. Was it unreasonable to ask whether the ratios governing planetary motion might be similarly organized? Whether the vast, slow movement of the celestial bodies might stand in relationships that a sufficiently attentive mind could recognize as harmonious, in the same way and by the same mathematics that governed the intervals between the strings? This is not a mystical question. It is a mathematical one. It asks whether the same law that governs the small, the string, the hammer, the brief vibration of air, also governs the large, the orbit, the period, the measured distance between one sphere and the next. The Pythagorean answer was yes, and the Pythagorean understanding of why the answer was yes was grounded in the same observation that had started everything, that the physical world, at the level of vibrating lengths, is organized by simple mathematical ratios, and that this organization is not local but cosmological, not a property of strings specifically, but a property of the order underlying all physical arrangement. The vibrating string becomes, in this view, a small and accessible example of a principle that operates everywhere the universe has organized itself in proportioned relationships. The monochord is a window, not an endpoint. What it shows, when examined closely, is a glimpse of the same structure that the planets enact across the vastness of their orbits and the depth of astronomical time, the structure of mathematical proportion, operating at every scale, governing the intervals between notes and the intervals between worlds with the same simple, persistent, indifferent law. A teacher stands outside in the evening in the open air of Croton and points at the sky. The planets are visible, several of them, their light steady and unwavering in the way that distinguishes them from the stars. He points at one and names it. He names the next, and for each one he says something about the interval it sustains, the note it contributes to a harmony too large and too slow for any human lifetime to hear in full, but no less real for that. The student beside him looks up. He has spent days with the monochord. He knows the feel of the fifth and the fourth and the octave in his hands and in his ears. He knows the way consonance settles and dissonance reaches. He knows the mathematical relationships that underlie the experiences. And now, standing in the open air with the planets arranged above him in their slow and ancient courses, he is being asked to extend what the string taught him into a register so large that no instrument can measure it and no ear can hear it, to understand that the same principle governing the narrow board and the single vibrating string might also govern the distances between those steady lights, might express itself there in ratios as simple and as precise as 2, 1 and 3, 2, might produce in the silent spaces between the spheres harmonies as real as the ones he has spent days carefully listening to. He does not know whether this is true. He cannot verify it the way the monochord verifies the intervals. But he has learned something in those days, with the string that makes the extension feel less like speculation and more like the continuation of a pattern that began the moment the first ratio was confirmed. The sense that the physical world is not indifferent to mathematical proportion, but organized by it. That the order is not imposed on the world from outside, but found within it. That every measurement taken carefully enough will eventually find, beneath the specific numbers, the same simple relationships that the string has been patiently demonstrating all along. He looks at the planets. He thinks about ratios. The teacher beside him says nothing further. The evening deepens around them both, and the stars behind the planets multiply, and the whole vast structure of the sky turns with the slow patience of something that does not need to be told to move, does not need to be maintained or reminded, simply continues, as it always has, in the great proportioned course of its own law. From the string to the sky, the Pythagoreans followed one observation as far as it would go. They began with what the ear could hear and what the hand could measure: the width of a bridge on a narrow board, the position of a finger on a string, the ring of a specific interval in the air of a small room. They followed the numbers in those measurements and found that they were not arbitrary, not conventional, not chosen for convenience, but that they were the first 4 integers, the simplest ratios, the proportions that the ear had always already known were right. They took this discovery seriously as a discovery can be taken, and asked what it implied about the world in which the string vibrates and the hammer strikes and the note rises and fades, and the ear receives it and knows before any calculation whether what it has received is orderly or not. What it implied, they concluded, was that order is mathematical and that mathematics is real, not a tool the mind uses to describe a world that would be there without it, but the structure of the world itself, the principle by which the physical is organized, and the reason that beauty and sound is not a preference but a perception. The ear is a mathematical instrument, the string is a mathematical object, the consonance is a mathematical event, and the silence that settles over the room when a held fifth finally fades, the silence that follows the sound as its natural completion, as the room returns to the state the sound had briefly organized into beauty, is the silence of a world that was mathematical before any mind was present to notice it, and will be mathematical long after the last note has been played. The hammer stopped. The street went quiet. The philosopher stood for another moment in the ordinary afternoon light, listening to the echo of what he had just heard, feeling in the air around him the slight and precisely proportioned residue of a sound that had, for a moment, been right, right in the way that a key is right in a lock, right in the way that a proof closes, right in the way that a resolved chord settles into its final consonance and rests there, vibrating in the dark, still sounding the interval the mathematics required. The room around it holding the sound as it diminishes toward the threshold of hearing, and then past it into the silence that is not the absence of the sound, but the sound's continuation in a register the ear can no longer reach. And there, in the diminishing ring of that last interval, in the almost silence where the mathematics is still operating and the proportion still holds, and the ratio of the vibrating length to the whole string has not changed and will not change and was never going to change. The sky above the street was already organizing itself by the same law, in the same simple proportions, in the vast and inaudible music of its own slow turning. A Pythagorean teacher stands in the open air at the edge of the city, and the night above him is clear in the way that nights in the south of Italy can be clear, not merely dark but layered, the stars holding their positions with a steadiness that feels deliberate, each one placed where a long and patient arrangement has set it. His student stands beside him, younger, still learning to be still. The teacher lifts his hand and points toward a point of light, low in the west, burning with a faint reddish warmth, unhurried in its slow arc across the sky. He says that one sounds the interval of a third. He moves his hand to a brighter point overhead, white and unwavering. That one, he says, holds the fifth. The student looks upward and listens, which is the correct response, though he hears nothing. The teacher does not tell him this is a failure of attention. He tells him it is a fact about attention, about what immersion prevents, and what distance makes possible, and why these are not the same as hearing and not hearing. This is where the doctrine begins. Not with an equation or a theorem, not with a tablet of numbers or a stretched string in a workshop, but with two people standing beneath the sky, and one of them naming intervals in the motion of light. The idea that the celestial bodies in their courses produce a vast harmonic arrangement, that the planets move through the heavens in proportions that obey the same mathematical law that governs consonance and sound, is not a metaphor the Pythagoreans were reaching for. It was a literal claim about the structure of the world. The cosmos was not like a musical instrument. The cosmos was a musical instrument, playing a chord whose lowest note was the deepest thing any mind would ever encounter, and whose highest note was beyond the reach of any hearing that had spent its entire existence inside the sound. Philolaus was among the earliest of the Pythagorean thinkers to set any of this down in writing, and the fragments that survive from him describe a cosmological arrangement in which heavenly bodies are ordered around a central fire in patterns that reflect harmonic proportion. The details of his specific arrangement differ from the picture the later tradition would settle on, but the governing conviction does not differ. The bodies moving through the heavens are not moving randomly. They are not moving according to forces that are indifferent to proportion. They are moving in the way a well-tuned instrument's overtones move, each frequency related to the others, by ratios that are simple, whole, and beautiful in the precise sense the Pythagoreans gave to that word, which was not an aesthetic judgment, but a mathematical one. Beauty, in this tradition, was the name for what happened when proportions were right. It was not a feeling layered over a neutral structure. It was the structure itself, perceived by a mind that had become quiet enough to receive it. What the teacher is explaining to his student that night in Croton is therefore not a poetic vision of a musical universe. He is explaining a cosmological fact, and he is explaining it the way one explains any fact that requires preparation to receive, by standing outside with a patient person and naming what is present, one point of light at a time, till the pattern begins to accumulate in the mind, like the notes of a melody that only becomes recognizable after the third or fourth repetition. The student may not hear the chord the planets are sounding, but he is being taught to understand what it would mean to hear it. He is being taught the shape of the silence in which it lives. Aristotle, sitting in Athens 2 centuries after Pythagoras, had thought carefully about this silence, and his response to the doctrine is one of the more philosophically interesting moments in his account of his predecessors. He did not dismiss the claim that the celestial bodies produce sound in their motion. He considered it with the seriousness it deserved. Bodies of that mass moving at those speeds, through that distance, If anything were to produce sound, these would. The reasonable objection to the Pythagorean doctrine was not that it was fanciful. The reasonable objection was simply that no one could hear it. And Aristotle's answer to that objection, the answer he attributed to the Pythagoreans themselves, is a piece of philosophical reasoning that turns the absence of evidence into something more complex than it first appears. The music of the spheres is inaudible, he reports them saying, not because it is not there. It is inaudible because it has been sounding without a single moment of interruption since the very beginning of each human life. Every person who has ever lived has been inside this sound since the first breath they drew. There has never been a contrasting silence, never a moment in which the cosmic chords stopped and then started again, never the gap that would allow a human ear to register the difference between its presence and its absence. Hearing depends on contrast. We perceive a sound because it rises from a background that had been, a moment before, quieter. But the music of the spheres has no such background. It has always been the background. And so the ear, immersed in it from the first instant of existence, has simply adapted, not learned to ignore it, but lost entirely the capacity to distinguish it from silence, because for a creature who has heard nothing else, silence and this particular sound are experientially the same. This is a philosophically precise argument. It is not a mystical evasion of the problem. It uses the psychology of perceptual adaptation, the way any constant stimulus eventually recedes below the threshold of notice, to turn an apparent objection into a subtler claim about the limits of unaided attention. The evidence against the Pythagorean doctrine turns out, on this reading, to be the doctrine's own prediction. Of course no one can hear it. What would make a person expect that they could? The ability to perceive the deepest order of the cosmos has never been a default condition of human awareness. It has always required something: practice, discipline, the long cultivation of a particular quality of interior stillness. The music is not absent from experience. It is present in a way that ordinary experience is constitutionally unequipped to receive. The student standing beside his teacher that night is not expected to hear it. He is expected to begin the work that might, over years, make a different quality of hearing possible. The naming of intervals, this one a third, that one a fifth, is not a description of what he is currently perceiving. It is the beginning of a training. The teacher is giving him a map of a territory he has not yet entered, and the gift is not the map itself, but the knowledge that the territory is there. Plato had spent time among Pythagorean thinkers in the south of Italy, and what he brought back from those encounters shaped some of the most mathematically intricate writing he ever produced. In the dialogue the tradition has come to call the Timaeus, he set down an account of how the cosmos was made, and at the center of that account is a construction that is, in its essential structure, a tuning of the world. The figure Plato calls the demiurge, a craftsman rather than a creator in the absolute sense, working with materials already given rather than summoning something from nothing, divides the stuff of the world soul into portions according to a specific mathematical sequence. The ratios he uses are the ratios of the Pythagorean musical scale. The proportions into which the world soul is cut are the same proportions that govern the consonant intervals, the octave, the fifth, the fourth. The universe is not built like a musical instrument. It is built from the same mathematical relationships that musical instruments, when correctly made and correctly played, succeed in reflecting. Plato, at his writing table in the academy, surrounded by geometers and their diagrams, aware of the Pythagorean arguments he had been testing and extending for decades, pauses in the middle of this construction, not dramatically, simply the pause of someone checking a calculation against something that is not written on any scroll, a reference that lives in the understanding rather than the archive. The ratios he is working with are precise. The sequence of intervals into which the world soul is divided is not approximate or symbolic. It is mathematically specific. What he is describing is not an analogy between music and cosmology, a nice parallel drawn to illuminate both. He is asserting an identity. The mathematical law that governs harmony and sound is the same mathematical law that was used in the making of the world itself. The cosmos is harmonically structured at the level of its constitution, not at the level of its decoration. This is a strong claim. Plato knew it was a strong claim. The Timaeus is presented with more hedges and qualifications than most of his other dialogues, a story that is only probably true, an account offered as the most plausible rather than the certain one. But the hedging is about the limits of human knowledge in the face of a vast subject, not about the claim itself. Within those limits, he is saying something that he regards as genuinely true. The ratio 2. One is the octave, not merely in a stringed instrument, and not merely in the abstract. It is the octave in the structure of existence. The mathematical relationship that makes two sounds harmonious is the same relationship that makes two aspects of the cosmos ordered, and this is not a coincidence that requires explanation. It is on the Pythagorean and Platonic reading, the explanation, the deepest fact available about why any of this holds together. The myth of which Plato sets at the close of the Republic in a position of evident deliberateness, carries the doctrine into the territory of what a soul might perceive when freed from the particular deafness of embodied life. There's a soldier who dies in battle, who is allowed to observe the journey of souls through the afterlife before being returned to his body to report what he has seen. What he sees in the celestial portion of his journey is the arrangement of the spheres, each one a great whirl nested inside the next, turning at its own rate, and on each sphere a figure who is sustaining a single pure note. The notes together form the single harmonious chord of cosmic order, each voice contributing its one interval, none of them complete alone, all of them necessary to the whole. The souls traveling through the spheres hear this for the first time. Hear it, Plato implies, because they are no longer inside it. The constant immersion that had kept it below the threshold of embodied hearing is over. Without a body, without the noise of biological life, without the thousand small urgencies that fill a living day, there is suddenly the silence in which the chord can finally be distinguished from the background of which it had always been the deepest content. This is an eschatological vision built on a philosophical foundation. The claim is not merely beautiful, it is the Pythagorean doctrine of perceptual adaptation carried into a cosmological narrative. What the living cannot hear, the unencumbered soul can, not because the soul has been given some new faculty, but because the obstacle has been removed. The music was always there. It was the noise of embodied life that had covered it, and this is why the Pythagorean practices of silence, of mathematical contemplation, of the evening review, and the morning hymn were understood not as arbitrary spiritual exercises, but as preparations, partial, imperfect, but genuine, for a quality of attention that full embodied life rarely permits, and that only something like death makes complete. The figure who comes later in the tradition and takes this inheritance most seriously, most rigorously, most literally, with the most willingness to follow its implications into the technical mathematical specifics, is not a Pythagorean philosopher, but a 17th century German astronomer and mathematician who had spent a great deal of his life being too strange for comfort in almost any of the intellectual communities he encountered. Johannes Kepler believed in the music of the spheres. He believed in it not as a metaphor and not as a poetic inheritance. He was honoring out of respect. He believed in it as a mathematical truth, waiting for the right data to confirm it. And he spent the better part of 20 years looking for that data in the planetary observations that Tycho Brahe had accumulated over decades of patient, precise watching of the sky. The book Kepler published in 1619 is called the Harmonices Mundi, the harmony of the world, and it is, among other things, one of the longest sustained attempts in the history of science to demonstrate a specific numerical correspondence between the mathematical structure of music and the mathematical structure of planetary motion. He was looking for intervals, not metaphorically looking, not checking whether the solar system vaguely resembled a musical arrangement. He was calculating the actual ratios between the maximum and minimum orbital speeds of each planet, the speed at its closest approach to the Sun and its speed at its farthest point, and then comparing those ratios to the ratios of specific musical intervals. If the Pythagoreans were right, if the same mathematical law that governs consonance and sound also governs the arrangement of the heavens, then somewhere in Tycho's numbers the intervals should appear. Kepler, in his study in Linz in the winter of 1618, surrounded by tables of numbers, the ink cold and the candles burning low, he calculates the ratio of Saturn's maximum orbital speed to its minimum and finds something very close to 4, 5, a major third. He works through Jupiter and finds an interval near 5, 6, a minor third. Mars gives him something close to the ratio 2, 3, a fifth. He moves through the planets one by one, and what he finds is not perfect. The ratios are approximate. The intervals are not exactly the intervals of the scale he has been comparing them to, but they are close enough to be interesting, and the pattern of their correspondence is not random. The planets whose orbits are most nearly circular, whose maximum and minimum speeds are closest to each other, correspond to the smaller musical intervals, the tighter ratios. The planets whose orbits are most eccentric, whose speeds vary most dramatically between perihelion and aphelion, correspond to larger intervals, the wider ratios. The shape of the orbit is reflected in the shape of the musical interval. The geometry and the harmony are speaking the same language, but Kepler found something more than approximate interval correspondences. Working through the mathematical relationships between planetary orbits, driven by the conviction that these relationships must be expressible in simple mathematical form because the cosmos is harmonically ordered, he arrived at a precise mathematical law: the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This is what later centuries would call his third law. It is one of the foundational results of modern astronomy. It is the mathematical relationship from which Newton would eventually extract the inverse square law of gravitation. When it describes with complete precision and without any approximation a structural relationship that holds for every planet in the solar system, including planets Kepler never knew existed. He found it while looking for music. He found it while working through the conviction, Pythagorean, Platonic, ancient, and to most of his contemporaries slightly embarrassing, that the cosmos was built from harmonic proportions, and that a patient enough search through the right numbers would find them. The third law emerged from the Harmonices Mundi, which is to say, it emerged from an attempt to finish what Pythagoras had started, to find in the actual measured motions of the actual planets the mathematical structure that Pythagorean cosmology had always claimed was there. That this search produced one of the most important results in the history of physics is not an accident to be explained away. It is a philosophical fact about where the result came from and what kind of thinking made it possible. Kepler sat very still in the moment of finding it. This is not a detail invented for effect. It is the kind of stillness that belongs to any moment in which a long search arrives unexpectedly at its destination. The pen in his hand, the tables of numbers that had been Tycho's life's work spread across the desk, the specific quality of silence that follows the completion of something that had taken years. He wrote afterward, in the Harmonices Mundi itself, about the overwhelming sense of confirmation, not merely intellectual satisfaction, but the feeling of having touched something that had been real for a very long time before any human hand reached it. He compared himself to Pythagoras. He did not think the comparison was grandiose. He thought it was accurate. The philosophical question this raises, the one that the Pythagorean tradition has always raised, and that Kepler's work makes acute in a specific way, is the question of what it means for a mathematical structure to be discovered rather than invented. When Kepler found that the square of the orbital period is proportional to the cube of the orbital distance, was he finding something that had been true since the planets began moving, waiting there in the mathematics of their orbits for any mind that came equipped with the right questions? Or was he imposing a mathematical pattern on a set of measurements, finding order because the mind that was searching was a mind that expected to find order? The Pythagorean tradition has a clear answer. Number is not a human construction. Mathematical relationships are not conveniences humans have organized their observations into. The ratio 2, 1 is the octave. Not because Greek musicians agreed to call it that, not because of a convention that could have been otherwise, but because the physical behavior of vibrating strings under those proportional conditions produces, regardless of any human presence or preference, the specific acoustic result that the ear experiences as consonance. The consonance is in the ratio. The ratio is in the world. And if the ratio is in the world at the level of vibrating strings, there is no principled reason to believe it stops being in the world at the level of planetary orbits, or at the level of whatever larger structures surround those. What Kepler sat in the stillness of was the sense that the Pythagoreans had been right about this, right in a way that 2,000 years of intermittent doubt had not been able to fully dislodge, right in a way that his own discovery now confirmed from the inside by arriving at a mathematical truth through the path they had described, rather than arriving at it through any other path. He had looked for harmony and found law. The law was harmony. He had been following a 2,000-year-old hunch, and the hunch had led him to something that no merely empirical investigation, patient and precise as Tycho's observations had been, could have assembled on its own. It had required the philosophical conviction that the pattern was there, that the cosmos was structured by mathematical ratios, that the right question to ask of Tycho's numbers was a musical question. A contemporary reader closing the Harmonices Mundi late at night, aware that the planetary relationships Kepler described are still operating, still holding in precisely the proportions he found, still obeying the third law with complete mathematical fidelity. Whether or not any human calculator is at that moment checking the numbers might feel something the style guides of science do not easily accommodate. Not wonder exactly, or at least not only wonder, something more like the specific quietness that comes from recognizing that a particular piece of the world has been doing what it was doing long before it was noticed, and will continue to do it long after the last noticing. Saturn's ratio of maximum to minimum orbital speed was close to a major third before Kepler was born. It will continue to hold that proportion long after every copy of the Harmonices Mundi has deteriorated. The mathematics does not require witnesses to remain true. This is close to the Pythagorean understanding of number, not that human minds generate mathematical structure by imposing order on raw sensation, but that mathematical structure is simply there, and that human minds capable of sufficient attention can find their way to it. The cosmos was arranged harmonically before any ear was present to hear it, before any mind was present to recognize the intervals, before any philosopher was present to name the ratios and compare them to the notes of a scale. The arrangement is not for anyone. It does not require appreciation to remain what it is. It was sounding in the silence of a universe without observers, and it will sound in whatever silence comes after observers are gone. The Pythagorean teacher pointing at planets and naming intervals was not making a claim that required a human ear to be true. He was educating his student in the direction of something real, something that would continue to be real, whether or not the education succeeded, whether or not the student ever developed the quality of attention required to approach it, whether or not the Brotherhood at Croton continued to exist as a community in which such education was possible. The cosmos was not waiting for Pythagoreans in order to be harmonically structured. The Pythagoreans were waiting for themselves to become capable of perceiving what had always already been the case. The planets move on their measured paths through the great dark, and the ratios hold. The ratio of the period to the distance holds. The ratio of maximum to minimum speed holds. The orbits are not moving toward better intervals or more perfect consonances. They are doing what they were doing when the solar system was young and there was no life anywhere in it to calculate the proportions or feel anything about them. They are doing what they will do when there is no life left. The ratios are not diminished by the absence of witnesses. They are not enhanced by the presence of them. They simply hold the way a mathematical truth holds, not because anyone is enforcing it, not because it is useful, not because anyone has decided to believe it, but because it is structured that way, at a level below the level at which decisions can be made. And somewhere in the long history of the tradition that runs from the Pythagorean teacher pointing at stars in Croton to Plato's demiurge, cutting the world's soul into musical proportions, to the myth of Ur-souls, hearing for the first time what embodied life had always covered, somewhere in that long tradition, there is the patient and serious claim that the structure is available, that human attention, disciplined and quieted by long practice, can find its way toward it, not all the way, not from inside a body and an ordinary life, but far enough to feel the edges of something that has been present since the beginning. Kepler felt those edges on the night he found his law. To pen in his hand, the numbers on the table before him, the specific and unhurried quality of a confirmation arriving after years of sustained and faithful looking. He was not the first person to stand at that edge. The teacher and the student had stood there too, in the open air of a southern Italian night, one of them naming intervals in the light of moving worlds, both of them knowing that the sound was there and that the silence around them was not empty, but full of something that had been sounding since long before either of them arrived to listen, and that would go on sounding in the deep proportioned dark long after neither of them remained. The planets hold their intervals. The ratios that Kepler found in Tycho's careful numbers are still operating in exactly the proportions he described, still tracing their paths through the mathematics of the solar system with the same quiet fidelity they have always had. The third law holds for Mercury and for Saturn, and for every body in between, holds without assistance, holds without witness, holds in the long, cold distances between the sun and whatever lies at the edge of what the sun's gravity organizes. No calculation is currently confirming them. No astronomer is at this moment checking the proportions. The ratios are holding in the silence the way a mathematical truth holds, the way the ratio 2 1 holds in every octave that is sounding anywhere in the world tonight, and in every octave that has sounded since the first string was plucked, taut, and divided, and in every octave that will sound when no living hand is left to do the dividing. The cosmos was, in some sense, obeying a musical law, long before any mind was present to hear it stated, long before any teacher was present to point at a point of light in a clear southern sky and say that one holds the fifth. The law was there, the interval was there, the proportion was there, in the slow and patient motion of a world that needed no audience to remain what it had always been. In the last light before the lamps were brought out, a member of the brotherhood would sit alone. The day was not yet finished in his mind. He had eaten, spoken with others, walked the usual paths between the garden and the hall, and now he sat at the edge of the evening with his hands resting open in his lap, doing something that looked from the outside like nothing at all. From the inside it was more deliberate than anything else he had done since waking. He was listening back, not to sounds still present in the air, but to the shape of the hours just past, the morning's study, the afternoon's conversation, the small choices made between one thing and another, reviewing each in the spirit, not of a judge assessing faults, but of a musician listening back to something they had played, attending to where the melody had held its course, and where, quietly, it had drifted from the interval it was reaching toward. This practice had a name within the brotherhood, though names mattered less than the habit itself: iamblichus. Writing centuries later from deep familiarity with the tradition, described the Pythagorean evening as a structured return, a deliberate retracing of the day's movements before sleep, an attempt to restore the soul's interior order before it passed into the night. The word he reached for was not moral accounting, it was closer to tuning. The way a musician, before setting down an instrument, might run through its range once more, not performing, simply listening, to confirm that the strings still hold their proper tension, and that the whole instrument is ready to be set aside in good condition. The soul, for the Pythagoreans, was something that could go slightly out of tune, not through wickedness necessarily, through distraction, through the friction of ordinary hours, through the simple wearing effect of moving through a day that did not arrange itself according to mathematical law. The soul arrived in the morning with whatever harmony its nature permitted, passed through the various irregularities of waking life, and arrived at evening somewhat changed, its tensions slightly altered, its proportions perhaps less clean than at the start. The evening review was the practice of noticing this, and through the act of noticing alone, of allowing the proportions to settle back toward their proper form. It was a quiet discipline. It asked for no speech, no confession, no reckoning with an external authority. It asked only for attention, the particular quality of attention that the Pythagoreans spent years learning to cultivate, and for the willingness to let what had happened in the day be seen clearly, without resistance, as if from a slight and comfortable distance. The silence required for this kind of attention was something the brotherhood took with exceptional seriousness. A new initiate arriving at Croton would be asked in the first years of his membership to do something that seemed at first like withholding, but revealed itself gradually as a form of deepening. He was asked not to speak, not for an afternoon, not for a week, but for a period of 2, 3, sometimes 5 years. He would sit at the edge of communal gatherings and listen, He would receive teaching without asking questions. He would observe the more advanced members of the brotherhood in conversation and hold inside himself whatever the conversation stirred without releasing it into words. The responses that formed and were not spoken did not disappear. They accumulated, turned over, refined themselves in the interior quiet, and arrived eventually at a quality of thought that had been worked all the way through before it ever reached the surface. This was not punishment and was not understood as deprivation. The silence was understood as the first and most necessary instrument of philosophical education, not the absence of speech, but the presence of a particular kind of listening, one that went all the way down through what was being said and into the structure beneath it. There is a difference between hearing words and hearing what the words are made of. Most ordinary conversation moves across the surface of ideas without pausing long enough to feel the proportions underneath. The required silence of the Pythagorean initiate was designed to slow this movement until the proportions became audible, until the student could hear, beneath any claim or question, the mathematical relationships that gave the claim its shape and the question its particular pull. After enough months in that silence, a quality of attention would begin to emerge that the student had not previously known he possessed. A listening that did not stop at the outer edge of what was being said, but continued inward, following the structure of a thought, the way a hand might follow the grain of a piece of wood, feeling, without looking, where the pattern ran and where it shifted. This was the attention the Pythagoreans believed was necessary before genuine philosophical understanding became possible. Not cleverness, not quickness, not the ability to produce a counter-argument before the first argument had finished. The ability to be still enough, long enough, that the structure of a thing could make itself felt. The silence was, in this way, the foundation on which everything else the brotherhood practiced was built. Before sleep each evening, a member of the brotherhood would sing. This too was a practice that Iamblichus preserved in his account. The community performed specific songs in the hours before sleeping, hymns constructed with deliberate attention to their harmonic properties, their intervals chosen for the quality of stillness they produced in whoever was sounding them. The purpose was not enjoyment, though enjoyment was not absent. The purpose was the same as the evening review, to bring the soul's proportions back into alignment before the body entered the night. The song was understood as a direct intervention in the soul's interior state, a tuning administered through the instrument of the voice, the vibrating air, the mathematical relationships embedded in the intervals between notes. The thinking behind this was as precise as it was strange to modern hearing. Sound, for the Pythagoreans, was not separate from number. Sound was number made audible, ratio made available to the ear, the way a geometric figure is made available to the eye. When a voice sounded the interval of a perfect fifth, it was not producing a pleasant combination of pitches. It was instantiating the ratio 3, 2 in the physical medium of vibrating air, and that ratio, entering the body through the vibration of bone and membrane, carried with it the mathematical property of the interval, its precise, clean proportionality, its quality of ordered simplicity. The soul, resonating sympathetically with that proportion, tended toward the same ordered simplicity in itself. This is what it meant within the tradition to say that music could heal or harm the soul. It was not a metaphor for emotional effect. It was a claim about how mathematical structure, instantiated in sound, acted directly on a soul that was itself constituted of mathematical relationships. A dissonant interval introduced disorder. A consonant interval restored proportion. The songs sung before sleep were chosen for the specific quality of resolution they produced. The sense, available to anyone who had sat long enough in silence to hear it, of competing tensions releasing into a state of proportioned stillness. The sound died away, and the silence that followed was different from the silence before. It was the silence after a chord has resolved. Not the silence of absence, but the silence of completion. The whole harmonic event present in the room, still, not as sound any longer, but as the quality of the air in which the sound had moved. A Pythagorean member, humming one of the evening hymns, following the sound as it faded, would stay with the silence that came after, as if it were the tone continuing at a frequency no longer audible, because within the terms of the tradition, it was. The mathematical relationship that had sounded in the room did not cease to exist when the vibration ceased. The proportion remained. The ratio held. Only the medium had gone quiet. This, the Pythagoreans believed, is what sleep is entered into. Not blankness, not the suspension of order, a state in which the soul, freed temporarily from the friction of waking sensory life, rested more fully within the harmonic structure that constituted it. The way a string, after sounding its complex of overtones, gradually settles back into its fundamental frequency, the deepest and most basic tone it is capable of producing. The overtones do not vanish because they are no longer heard. They are present in the fundamental, contained within it, as all the upper members of the harmonic series are present, mathematically, in the simplest vibration of the string. Sleep, approached through this tradition, was understood as a return to that fundamental, not escape from the mathematical order of things, settlement into it. There is a quality of attention that pure mathematical contemplation produces, and it is distinctive enough to have been noticed by many people across a very long span of time. A mathematician working alone, moving through the steps of a proof or the implications of a geometric relationship, will often describe arriving, at some point in the work, at a specific quality of stillness that has little to do with the difficulty of what they are doing. The self, the ordinary surface of anxieties and preferences and small habitual reactions, recedes. Attention expands into the structure of what is being contemplated. There is no longer an observer separate from the observed. There is only the structure and the attention moving through it, and a quality of spaciousness around the work that feels less like concentration and more like the absence of obstruction. The Pythagoreans would have recognized this description immediately. This is what they were pointing at when they recommended mathematical contemplation as a practice, not its practical applications, not its usefulness for measurement or commerce, but this specific experiential quality that it produced in those who followed it with sufficient patience and sufficient silence. The soul, engaging with pure mathematical structure, was engaging with the organizational principle of its own nature. The understanding that followed was not merely intellectual, it was participatory. The mathematician attending to a ratio was in some sense remembering what the soul is made of. This remained, for the tradition, not a poetic claim, but a precise one. The soul was constituted of mathematical proportions. The cosmos was constituted of the same mathematical proportions. Mathematical contemplation was the practice by which a soul already structured according to mathematical law turned its attention toward the mathematical law governing everything else, and recognized in that turning a correspondence so complete that it was impossible to say with confidence where the soul's structure ended and the world's began. Plato, who spent time with Pythagorean philosophers in the cities of southern Italy and absorbed more of their thinking than he always acknowledged directly, built his account of the world soul in the Timaeus on exactly this recognition. The demiurge in Plato's creation myth, the divine craftsman who fashions the cosmos from pre-existing materials according to the best rational plan, constructs the soul of the world using the same mathematical ratios that govern musical tuning. The world soul, before it is given a body, is divided and arranged according to the proportions of the harmonic series. The ratios 1, 2, 4, 8, and 1, 3, 9, 27, with the intervals between them filled in according to the relationships governing the perfect fourth, the perfect fifth, and the octave. The soul of the cosmos, in other words, is a musical instrument. Its inner constitution is harmonic, and the souls of individual beings, fashioned from the same mixture as the world soul, but in diminished form, carry within them the same proportions in smaller expression. This means, within the Platonic and Pythagorean framework, that when a human soul attends to a musical consonance and feels it as beautiful, when the interval of a fifth or a fourth or an octave strikes the ear as right, as possessed of an order that mere agreeableness does not explain, what is happening is a recognition. The soul is recognizing, in the external proportion, the proportion that constitutes its own innermost structure. Beauty, in this tradition, is not subjective preference. It is the soul's accurate perception of its own nature, reflected in the world outside it. The implications of this spread outward in many directions and do not all arrive at comfortable conclusions. But the central movement from the felt experience of musical consonance to the recognition of a shared mathematical structure between perceiver and perceived has the quality of something that once clearly seen cannot be unseen. The contemporary philosopher or mathematician who encounters these ideas for the first time sometimes dismisses them as the understandable but superseded attempts of ancient thinkers to make sense of a world they lacked the tools to understand correctly. This response is too quick, and it misses something that has not gone away. Roger Penrose, writing in the late 20th century, found himself unable to give an account of his mathematical experience that did not include something very close to the Pythagorean intuition. Mathematical structures, Penrose argued, are not invented by human minds. They are discovered. The explorer of number moves through a territory that was fully formed before any human expedition arrived, a vast, silent, already existing landscape of relationships and truths that hold whether or not any mind is currently attending to them. The Pythagorean theorem was true before Pythagoras. The ratio of a circle's circumference to its diameter was irrational before any geometer confirmed it. The prime numbers extended outward in their particular, irregular distribution before anyone had counted far enough to see the pattern. Kurt Gödel, working in the middle of the 20th century on the foundations of mathematics, held a similar position with unusual philosophical clarity. Mathematical objects, Gödel maintained, are as real as physical objects. The experience of mathematical understanding, the sense of perceiving a truth that one did not make, is epistemically genuine. The mathematician is not constructing, the mathematician is finding, and what is found was already there, complete, organized, patient. The position these thinkers hold is called mathematical Platonism, because its clearest ancient ancestor is Plato's theory of forms, but its actual origin in the tradition goes deeper than Plato. The Pythagoreans held this conviction before Plato gave it its philosophical architecture. Number, for the brotherhood at Croton, was not a human tool for organizing experience. Number was the substance of which experience was organized. The distinction matters. A tool exists because a craftsman made it and uses it. A substance exists on its own terms, prior to any particular use, and the craftsman who understands it well is working with something that has its own requirements, its own resistances, its own inner law. When Penrose describes the territory of mathematical truth as vast and silent and already fully formed, he is using language that would not have surprised a Pythagorean initiate in his third year of required silence. The territory is vast because the implications of even simple numerical relationships extend outward without limit. It is silent because it does not announce itself. It waits to be attended to, and it was already there before any particular mind arrived at its edge and began to explore. The mathematical relationship does not require anyone to notice it in order to hold. This is perhaps the deepest intuition the Pythagorean tradition carries. The ratios are not relationships between human concepts. They are relationships within the nature of things, within the intervals of sound, within the orbits of planets, within the proportions of organic forms, within the structure of whatever it is the word number is pointing at when it gestures past its ordinary uses toward what it really means. And those relationships hold in silence, in the absence of any observer, in the long stretches of time before any creature capable of counting had yet developed the capacity to count. The Pythagorean morning oath was taken before the tetractys, the triangular arrangement of 10 points in rows of 1, 2, 3, and 4, and the oath invoked the tetractys as the thing that contained the principles of all things, not the symbol of those principles. The principles themselves, arranged in a diagram small enough to draw in dust, the 1 point that generates the 2 that generates the 3 that generates the 4, and the 4 whose sum returns to 10, which is the completion of the first cycle of number from which all further number proceeds. Within those 4 rows of points, the Pythagoreans saw the ratios governing the octave, the fifth and the fourth, 2, 1, 3, 2, 4, 3, and within those ratios, the harmonic structure of the world. A student who had spent enough years in the required silence, attending to that diagram with the full quality of attention the silence had taught him, would begin to see it differently from the way it appears at first encounter. At first, it is an arrangement of 10 dots in a triangle, a simple enough figure, geometric and clean. After years of patient attending, it becomes something else, not because the diagram has changed, but because the attention has deepened enough to follow what the diagram is actually indicating. The proportions within those rows of points are the proportions within the vibrating string. The proportions within the vibrating string are the proportions within the movements of the heavenly bodies. The proportions within the movements of the heavenly bodies are the proportions within the soul, and the soul looking at the diagram is looking at its own structure, arranged in dust, small enough to cover with one hand. The size of the figure is part of the point. The organizational principle of everything that exists is small enough to hold in the palm. There is a specific quality to the kind of stillness that mathematical understanding produces, and it is different from the stillness of exhaustion, or the stillness of distraction, or the stillness of having simply run out of things to think about. It is the stillness of a mind that has followed a structure all the way to its own conclusion, and arrived somewhere that feels precisely and without exaggeration like an ending that was always already prepared. The proof closes, the proportion resolves. The ratio that was being sought turns out to have been present in the beginning, waiting in the initial conditions for the right series of steps to make it visible. A mathematician working late, reaching the point in a proof where the structure finally closes, where the last line follows from the line before it with the clean inevitability of a fifth resolving to its tonic, will sit back in a specific quality of silence that feels less like the cessation of thought and more like its completion. The work is not suspended, it has arrived, and the silence around the arrived work is not empty silence. It is the silence that surrounds something that has reached its proper form. The Pythagoreans understood this silence as the goal of mathematical practice, not the proof itself, the completed argument, the demonstrated relationship, but the quality of interior stillness that the completed argument produced in whoever had followed it with genuine attention. This was what all the years of practice, all the silence, all the evening review, all the singing before sleep were in service of the gradual cultivation of a soul that could hold mathematical structure with enough stillness that the structure had room to reveal its full implication, and enough patience that the implication, arriving slowly, was not rushed past on its way to somewhere else. The soul in that stillness is not doing nothing, it is doing the most precise thing it can do. It is attending to what is actually there, the proportion, the ratio, the relationship that holds whether or not this particular mind is currently tracing it, and in attending, participating in something that extends far beyond any single act of attention. The cosmos, within the Pythagorean framework, has been sounding its fundamental harmony since before any creature was present to hear it. The planetary movements, the intervals of the heavenly bodies against the silence of space, the vast slow chord that Pythagoras called the music of the spheres, all of this has been proceeding according to the same mathematical law that governs the vibrating string on the monochord, the same simple ratios contained within the 4 rows of the tetractys. Kepler, standing at the threshold of modern astronomy and unable to give up the conviction that the cosmos was organized harmonically, found within his own data exactly what the tradition had promised him. He would find a mathematical relationship between the periods and distances of the planets, precise enough to serve as the foundation of celestial mechanics, arrived at through a search for harmonic proportion in the ratios of orbital velocities. He did not think he was inventing the relationship. He thought he was finding it, and when he found it in 1618, after years of searching through Tycho Brahe's meticulous observations, the experience he described was not the triumph of having constructed something new, but the recognition of having uncovered something that had always been there, patient in the numbers, waiting for someone with enough preparation and enough willingness to look. The cosmos was obeying this law before Kepler traced it, before Plato described the world's soul according to harmonic ratios, before the Pythagoreans gathered in their hall at Croton and sang the evening hymns and sat in the particular silence of people who have spent years learning to hear what is beneath the surface of sound. Before any of this, the proportions held, the ratios governed, the fundamental frequency sounded into the surrounding quiet, and the surrounding quiet held it, and the whole arrangement proceeded according to its own mathematical law, indifferent to observation, complete in itself. This is not a cold image, though it might at first seem like one. The indifference of mathematical law to any particular observer is not the indifference of dismissal. It is the indifference of completeness, of a thing that needs nothing added to it to be what it is, that is not made more real by being noticed, that was fully itself before any noticing was possible, and will be fully itself long after the last noticing has passed. A soul entering sleep within the Pythagorean framework is moving toward this completeness, not abandoning the mathematical structure of the cosmos, but settling more fully within it, the way a string, plucked and set vibrating through its complex of overtones, gradually releases the higher, more agitated frequencies and settles into its fundamental. The fundamental is not less than the complex overtone pattern. It is the foundation that was always present beneath the complexity. The overtones ride on it. The whole vibrating system rests on it. When the overtones fade and only the fundamental remains, the string has not lost anything. It has returned to its own deepest nature. The Pythagorean initiate, after years of silence, after the evenings of review and the hymns before sleep, was attempting to become something like that string, not to eliminate the complexity of waking life, the various overtones of thought, desire, conversation, perception, but to deepen the fundamental within himself sufficiently that the complexity could rest on something proportioned and stable, something that held its tone through the ordinary friction of the day and could be returned to reliably in the evening's quiet. The mathematics was not separate from the practice. The mathematics was the practice. To understand ratio was to understand what the soul was made of. To contemplate the tetractys with genuine attention was to feel in the quality of the attention itself the mathematical order that the diagram was indicating. To sing the evening hymns and follow the intervals with a listening that had been deepened by years of silence was to instantiate in the air of the room and in the vibration of the body the same proportional relationships that governed the movement of the heavens. The practice and the cosmology were one thing. This unity between what is thought and how one lives, between the mathematical order of the world and the daily discipline by which the soul returns to its proper proportion, is the inheritance the tradition carries, and it has not grown less interesting with time. It has, if anything, grown more interesting as the distance between mathematical understanding and the rest of human experience has widened. The Pythagoreans did not experience that distance. For them, the number was not separate from the sound was not separate from the soul was not separate from the cosmos, and the cosmos was not separate from the quiet in which it moved. All of these were expressions of the same underlying proportional structure, available to attention at every scale, from the single string to the orbiting sphere. To hold this view, to inhabit it, even temporarily, with the quality of attention it asks for, is to feel something loosened in the way the mind ordinarily holds itself. The urgency that attaches to the surface of things softens the small irregularities of the day, which in ordinary attention seem significant in proportion to how recently they occurred. Take on the quality of overtones in a vibrating system, present, real, part of the complex whole, but not the fundamental, not the thing on which everything else is resting. Beneath them, steady and patient and indifferent to whether it is currently being noticed, the proportion holds. The ratio that makes the octave is 2:1. It was true before anyone plucked a string to confirm it. It will be true when no string is left to pluck. The relationship between those two numbers is not a human discovery in the sense of a discovery that could have been otherwise. It could not. The octave is the octave because of what numbers are, and what numbers are does not change with observers or with time. Somewhere in the night, a Brotherhood member finished his evening hymn and held the last note until it was no longer a note, until it had dissolved into the resonant air of the room and sat in the silence that followed, not waiting for anything, not reviewing, simply present in the residue of the sound, the quality that remained in the air after the vibration had ceased, the trace of the proportion that had sounded. He would have known, within his tradition, that this quality was not imagined. The room had been changed by the sound that had moved through it. The ratios were still present, in the silence, as they had been present in the sound, as they were present in him, as they were present in the slow movement of the stars beyond the roof of his small room, their intervals holding their proportional relationships in the vast surrounding quiet of the night. He would have understood, settling into sleep, that he was not leaving the order of things. He was returning to it more completely than the day permitted.